What happens when you add just a single methyl group to a phenethylene molecule? It sounds like this microscopic, almost insignificant change, right? But what if I told you that in the world of pharmacology, the tiniest molecular tweak can create massive ripples in human biology? We're talking about the ultimate biochemical butterfly effect. Today, we're looking at a compound that takes everything we thought we knew about a specific class of designer drugs and flips it entirely upside down.
Today's explainer is all about the 2CG anomaly. We're going to explore a substance that's honestly a total clinical and forensic mystery. It's a compound that literally rips up the established rulebook of biochemistry, completely defying what researchers and toxicologists expect.
Okay, let's dive into this. Here's our roadmap. We'll start with the 2CG anomaly itself, then look at its structural fingerprint, unpack the wild 30-hour mystery, check out its insight-enhancing profile, and wrap up with its real-world forensic utility.
Part 1. The 2CG Anomaly. Establishing the baseline. Before we can really appreciate why our subject today is such a wild outlier, we kind of need to understand what normal looks like for this family of chemicals.
So the foundation here lies in the 2C family. As you likely know, this is a series of psychedelic phenethylamines first synthesized and famously chronicled by chemist Alexander Shulgin back in his 1991 book PHKAL. Structurally speaking, the absolute core defining characteristic of the 2C family is the presence of methoxy groups at the 2 and 5 positions of a benzene ring. For decades, this specific framework served as a super predictable standard playground for pharmacologists.
But then we have 2CG, also known by its CAS number, 327715-14-4. 2CG is this unique phenylethylamine that completely defies the standard analytical and pharmacological expectations of its molecular cousins. I mean, it doesn't act like the rest of the 2C family, it doesn't look exactly like them in forensic testing, and its behavioral effects on humans, wildly divergent.
Moving on to part 2, the structural fingerprint. Zooming in on the molecule, let's uncover this specific tiny deviation that causes 2CG to act so strangely.
In the complex world of organic chemistry, the exact positioning of atoms is everything. Now, what's really interesting about this slide is those two numbers right there, 3, 4. They represent the unique structural key that unlocks 2CG's totally bizarre profile.
Let's contrast this with the baseline. 2CG actually has methyl groups attached at both the 3 and 4 positions of the phenyl ring. But if you look at the rest of the 2C baseline analogs, we're talking 2CB, 2CI, 2CD, they all feature just a single position substitution, usually just at the 4 position, like that single bromine atom in 2CB. 2CG is literally the only member of the 2C series rocking this dual methyl substitution at the 3 and 4 positions.
So what does that actually mean clinically? Well, this microscopic variation completely changes the physical mechanics of how the molecule behaves. This 3,4-dimethyl pattern alters the molecule's conformational flexibility, basically how it bends and moves. It changes its lipophilicity, or how it dissolves in fats. And crucially, it changes its steric interactions. That just means how its physical shape physically fits into the human body's serotonin receptors. Think of it like taking a normal house key, adding a tiny bump of metal, and then trying to force it into the lock. It behaves entirely differently.
Part 3. The 30-hour mystery. The pharmacokinetic anomaly. Here's where we transition from the microscopic structure to the macro-level physiological effects. Specifically, we've got to talk about this drug's exceptionally long duration of action.
And this brilliantly illustrates the sheer scale of the anomaly. It's staggering. While a compound like 2CD lasts a relatively brief 3 to 5 hours, and common ones like 2CB or 2CI last maybe up to 12 hours, 2CG has an active window of 18 to 30 hours. That's up to 10 times longer than some of its closest relatives.
No way, right?
So, how is a massive extension like that even possible? Well, it comes down to a fascinating 3-step biological roadblock. Step 1. That dual 3,4-dimethyl pattern we talked about creates extra physical bulk on the molecule. Step 2. This bulk creates what chemists call steric hindrance. It essentially acts like a physical shield, blocking access by monoamine oxidase, or MAO enzymes in the body, whose whole job is to break the molecule down. And step 3, because those enzymes can't easily reach the molecule to break it down, a process called oxidative deamination, the active half-life of the drug is drastically extended. The body literally just struggles to clear it out. Which brings us to part 4, an insight-enhancing profile, breaking the potency rules.
You see, it's not just the duration that's weird here. 2CG also fundamentally breaks the rules when it comes to potency and qualitative effects.
Normally, in this chemical family, the phenylethylamine version of a drug is way less potent than its heavier amphetamine counterpart. But 2CG? It requires an active dose of 20 to 35 milligrams, which is nearly identical to its amphetamine cousin DOG, also known as Ganesha. Plus, while standard analogs like 2CB and 2CI give you prominent visual effects, the visual effects of 2CG are either totally muted or completely absent, and that's despite its high potency and serotonergic activity.
Because it lacks those traditional visual hallucinogenic properties, Alexander Shulgin specifically categorized 2CG with a really unique label in his 1991 book, PI-HKL. He called it an insight enhancer. This brings a very qualitative human observation to all this dense pharmacological data. It's a compound that acts on the mind, deeply and for a very, very long time, but entirely bypasses the visual distortions you'd normally expect from this chemical class.
And I should briefly mention, this molecular branch extends even further. Shulgin actually synthesized several homologs of 2CG. You've got 2CG3, which lasts 12 to 24 hours, 2CGN, which causes amphetamine-like stimulation for 20 to 30 hours, and most astoundingly, 2CG5, which pushes the duration envelope to a staggering 32 to 48 hours. Seriously, up to 48 hours.
Finally, Part 5, Forensic and Research Utility, Real-World Applications. Let's look at how this unique biochemical fingerprint is actually used in modern science and law enforcement today.
So, the crucial point is this. 2CG absolutely cannot be swapped out for other 2C compounds in a lab. Because of its unique structure, it produces distinct retention times in chromatography and highly differentiated receptor binding profiles. It also creates unique mass spectral fragmentation patterns. Basically, when a lab machine blasts the molecule apart to see what it's made of, 2CG shatters in a completely unique way. If a forensic toxicological lab suspects designer drug intoxication involving this chemical, they definitely cannot just use 2CB or 2CD as a stand-in to calibrate their machines.
To solve this problem, scientific suppliers produce 2CG hydrochloride. This is a highly pure, stable crystalline solid that serves as a certified reference material, or CRM. Having this exact hydrochloride salt form allows researchers to precisely and traceably calibrate their forensic equipment. And this exactitude matters tremendously in the real world. Accurately quantifying the substance in biological matrices, like hair, blood, and urine, ensures medical accuracy when treating overdoses, and it prevents false positives or wrongful accusations in legal settings.
Now, because of its potency, it is heavily regulated. But the approach actually varies internationally. The United States classifies it as a Schedule I controlled substance, but interestingly, they classify it legally based on its status as a positional isomer of other controlled substances, like 2CE and DOM. Meanwhile, in Canada, it's explicitly listed as a Schedule III controlled substance.
We started this explainer by asking what happens when you add a single methyl group to a molecule. And as we've seen, it dramatically altered potency, entirely stripped away visual effects, and extended the duration of action by a massive factor of 10. It really makes you wonder, doesn't it? What other pharmacological secrets are hiding in the subtle, microscopic structures that bind to our minds?